In this lesson, we're going to implement the read side of the system. For the sake of simplicity, we will use the same application for both the read and write sides to avoid the need for setting up a message broker to communicate between services. In a real-world scenario, we would want to have a separately deployed service for the read side, which would subscribe to the events published by the write side. In this course, we'll be keeping things simple, but we wanted you to be aware that ideally you would want to have that separation. Alright, so let's get started. For the read side, we'll use the MongoDB database to store denormalized views of the data. To integrate with MongoDB, we'll use the Nest.js Mongoose package and install it by running the following command. Once the installation is complete, let's update our Docker Compose YAML file to include the MongoDB service. Let's save our changes, head over to the terminal, and start the MongoDB service by running the Docker Compose up-d read-db command. Next, let's navigate to our core module file and import the Mongoose module when the driver is set to ORM. Great! So now, if someone selects ORM as the driver, the system will use MongoDB for reads and Postgres for writes databases. While with the in-memory driver, it will use the in-memory collection for both the read and write sides of our system. Now, to better understand why having a separate read-only data source may be useful, let's add a few more attributes to the alarm entity. Okay, so we added 3 new attributes to our alarm entity here. Triggered at, which is the date and time when the alarm was triggered. Is acknowledged, a Boolean flag indicating whether the alarm has been acknowledged. And items, which is a list of alarm items or alarm triggers that triggered the alarm. Since we don't have the alarm item entity yet, let's go ahead and create it now. With this entity in place, our write-side database schema will have 2 tables now, alarms and alarm_items. The alarm_items table will have a foreign key to the alarms table, indicating which alarm the specific alarm item belongs to. Let's now create the denormalized alarm schema for the read side of our system. Inside the new schemas folder, let's create a new file called materializedalarmviewschema.ts and add the following code inside. As we can see, the materialized alarm view schema embeds the items attribute, which means that the materialized alarm view document will contain all the information right away, without the need to join the alarm items table, which will help speed up our read operations. While this is still a very basic example, it somewhat demonstrates the benefits of having a separate read-only model. In a real-world scenario, entities consist of many more attributes, and that is where CQRS really shines. For example, an alarm entity could have a metadata attribute, which would contain a lot of information about the alarm, such as the location of the alarm, the name of the device that triggered the alarm, and the name of the supervisor who acknowledged the alarm, etc. This information might be required by other services that operate on reported alarms, let's say to perform their own business logic. But only a few attributes are required to display the alarm on the UI. This is just an example of how having required data baked in could really help our performance. Okay, so before we move on, let's also update the in-memory driver to contain a new alarm item entity. Let's also update the alarm entity to contain some new attributes. Excellent. With this change in place, our infrastructure layer is all set. There are a few more repetitive tasks we need to do before we can start implementing the read side of our system though. Let's start by heading over to our domain layer and let's create a new domain class called alarm item and add the following code inside. As you may have already noticed, with DDD, everything is strictly organized and layers don't leak into each other. Infrastructure-related annotations are only used in the infrastructure layer. Data transfer objects with validation rules reside in the presentation layer, etc., etc. While this does make our codebase more verbose and easy to navigate, it also requires a lot of boilerplate code and introduces a lot of redundancy. And that's why it's always important to make sure that the benefits of using DDD outweigh the drawbacks for any specific use case. Alright, so let's head over to the alarm TS file and update the alarm class to contain the new attributes as well. We're also going to move the name and severity attributes out of the constructor signature and just keep the ID parameter there. With these properties in place, we'll declare two new public methods, acknowledge and add alarm item. The acknowledge method will simply set the isAcknowledged flag to true, and the add alarm item method will add a new alarm item to the items array. Great, let's save our changes and open up the alarm factory file now. In here, let's update the method signature to accept two new arguments, triggered at and items. Next up, let's update the create method to assign the triggered at attribute to the alarm instance. Also, let's not forget to iterate over the items array and add each item to the alarm. Excellent. Now, onto the mapper classes. First, let's focus on the ORM driver. In the toDomain method, let's make sure we assign all alarms attributes to the alarm object. And last but not least, let's map alarm items to the domain model. Great. Now, let's scroll down to the toPersistence method and update it to map all new attributes. Let's save our changes and real quick do the same thing for the in-memory driver. Perfect. Please note that the reason we have to update so many files is because we are supporting two different drivers. If we were to use only one driver, which is the case in most real-world applications, we would spend a lot less time on these repetitive tasks. We're showcasing the power of all these advanced architectural patterns in this course, so that's why we have a few of these additional steps. Alright, so with that out of the way, let's now move on to the application layer. Currently, our create alarm command exposes only two attributes, name and severity. Let's update it to expose the new attributes as well. Great! Now, inside the create alarm handler class, let's update the execute method to pass the new attributes to the alarm factory create method as well. Last but not least, let's update our create alarm DTO class to expose these new attributes. We could also add some validation rules here. And in a real-world application, you would surely want them. But since validation isn't the focus of this course, we'll skip this step. But please refer to the Nest.js Fundamentals course if you need a refresher on validation. Alright, excellent. Lastly, let's save our changes and head over to the alarm controller file and update the create method to pass the new attributes to the create alarm command constructor, and we should be all set. There's just one final step though. We need to let TypeORM know about this new entity. So let's go ahead and add the alarm item entity to the TypeORM for feature array in the ORM persistence module file. And finally, our application should be able to compile again. Just to double check, let's open up our terminal and first recreate our containers so we don't have any old entries in the database. We can achieve this with docker compose down, remove orphans, and then do docker compose up -d again. If we switch to the other terminal window, Let's see if we haven't missed anything. So far, everything looks good to go. If you're seeing any errors here, make sure you follow all the steps above. All of the code we've manipulated and the file names can be found below the course video, as always. Since our application now uses two different data stores, we'll split our repository to two individual abstract classes: Find Alarms repository and Create Alarm repository. Also, note that our Find Alarms repository will return objects that fulfill the Alarm Read Model interface. So for this, inside the domain folder, let's create a new folder called read-models, and inside of it, let's create a new file called alarm.read-model.ts. This class will represent the read model, which is optimized for read-intensive operations, such as queries, reporting, and presenting data to users or external systems. It is distinct from the domain model, which is optimized for write-intensive operations and encapsulates the core business logic and behavior of the domain. The main purpose of a read model is to improve query performance and provide a more efficient way to access data for specific use cases. By denormalizing, aggregating, or tailoring the data to fit the specific requirements of a read operation, read models can significantly reduce the complexity and time required to retrieve information. While in the case of our demonstration application, the read model here is almost identical to our domain model, in real-world applications, this would rarely be the case. So even though it may seem as if we introduced a lot of unnecessary redundancy in our application here, this most likely won't be the case in production apps, where read models, domain models, and even database schemas are often very different from one another. Alright, so let's get started here. Let's open up the Alarm repository file and update the class name to Create Alarm repository. Let's also remove the findAll method since we don't need it anymore. Lastly, let's rename the file itself to createalarmrepository.ts. Next to this file, let's create a new port called findalarmsrepository.ts and define the findalarms repository interface. The difference between these two is simply that one is responsible for writing data and the other is responsible for reading it. Also, as we mentioned earlier, FindAlarm's repository will return objects that fulfill the Alarm Read Model interface. We'll also need another port for inserting materialized alarm views into the read side database. So let's create a new file called upsert materialized alarm repository and define the upsert materialized alarm repository interface. Let's save our changes and head over to the getAlarms query handler file and update its constructor to inject the FindAlarms repository port. Let's also make it return Alarm Read Model now as well. Otherwise, everything else should remain the same. Now, onto our infrastructure layer. Let's start with the in-memory driver as it will be a lot easier to implement. First, let's open up the in-memory alarm repository class and make it implement both the FindAlarms repository and upsert materialized alarm repository ports. Since we'll be using the same class for both reading and writing, let's declare a new property that will represent the materialized alarm views. Next, let's update the findAll method signature to return alarm read model. Also, let's update the method body to return an array of values from the materialized alarm views map. And lastly, let's add the missing upsert method. Great! Now onto the module file. Let's open up the in-memory persistence module file and update the providers array to provide the FindAlarms repository and upsert materialized alarm repository ports. Here, we're using the useExisting property to tell Nest to use the same instance of the in-memory alarm repository class for all ports. Let's also not forget to export them too. Great! Now onto the ORM driver. This one's going to be more complicated as we'll be using MongoDB for reading data. We've made a lot of changes so far, but don't worry, we're making great progress. We're almost there. Let's start by first opening the ORM alarm repository and remove the findAll method. Next, let's rename the class to ORM create alarm repository. And lastly, let's also update the name of the file to be create alarm repository ts. Next to this file, let's create a new file called findalarmsrepository.ts and define the ORM findalarmsrepository class. In this file, we're using the inject model decorator to inject the alarm mongoose model into the ORM findalarmsrepository class. Inside the findAll method, we're using the find method to retrieve all documents from the alarm collection. We don't need to perform any mapping here as the alarm schema is identical to our alarm read model class. Remember, this was actually the goal of using a separate data source with denormalized data. We're starting to see some of the benefits of that already. Great. Now, with this repository in place, let's create another port implementation for inserting materialized alarm views into the read side database. Let's create a new file called upsert materialized alarm repository.ts, and let's define the ORM upsert materialized alarm repository class. Similar to the previous repository, we're using the inject model decorator again to inject the materialized alarm view mongoose model into this class. Inside the upsert method here, you can see that we're using the find one and update method to insert a new document into the alarm collection. Unless there's one that already exists with the same ID in the collection, then we update it. We don't need to perform any mapping here as the materialized alarm view schema is identical to the alarm read model class. Now, let's open up the ORM persistence module file and update the providers array to provide newly created ports. Like before, let's again not forget to export them. And lastly, we need to import the mongoose module for feature method and pass the alarm schema to it as an argument to register the model as a provider. Excellent. We're almost finished now. The only thing we have left to do is to update the alarm created event handler file to insert the denormalized alarm document into the materialized alarm view collection. So let's open this file and inject the upsert materialized alarm repository port into the alarm created event handler class. Next up, let's update the handle method to insert the denormalized alarm model into the read side database. And that's it. As stated in the comment here, in a real-world application, we would have to ensure that this operation is atomic with the creation of the alarm. Otherwise, we could end up with an alarm that is not reflected in the read model, for example, because the database operation failed, leading to an inconsistent state. But how could we even implement this? Well, if we had a message broker in place to communicate between the write and read side, we could use ACK and NACK to inform the broker about the success or failure of the database operation. If the database operation failed, the message would be requeued and retried later. If the database operation succeeded, the message would be removed from the queue. So to achieve this, we could also leverage the transactional outbox and inbox patterns. They are both unfortunately outside of the scope of this course, as they are quite involved. But we wanted to make sure we mentioned them and that it would be ideal to include some of these patterns in your application here. If you're interested in learning more about those patterns, check out our other course extension called Microservices, where we learn about and implement them. Alright, so back to our task at hand. Let's run the application and see if everything works as expected. Once the application is up and running, let's open up another terminal window and send a post request to the alarms endpoint to create a new alarm. You can find the curl command below the course video as always. And there we have it. As we can see, our alarm was successfully created. Now let's switch to the other terminal window and take a look at the logs. Great, no errors. So going back to our curl terminal, Let's send the GET request to the alarms endpoint to retrieve all the materialized alarm views. We're going to use the JSON_PP tool here to auto-format the JSON output, making it easier to read. If your operating system doesn't support this tool, feel free to omit that part of the curl command shown here. But fantastic, as we can see, we received one alarm item back with the embedded alarm items. We had to set up quite a bit of code in this lesson, but we did it. Great job. So to summarize, in this lesson, we've learned how to implement the read side of the CQRS pattern using Nest.js and MongoDB. Upon receiving an event, our system automatically creates a denormalized alarm view and stores it in the read side database. While this approach works and is commonly used in many applications, it introduces a lot of redundancy and can lead to inconsistencies if not implemented correctly. Also, we end up with multiple sources of truth, which can be hard to maintain down the road. This is why the CQRS pattern usually goes hand in hand with event sourcing, where instead of having the right side database, we store all events in an event store and use these events to build the read side database. This approach is of course more complex to implement, but it does have many benefits. Don't worry, we'll be covering this approach in the next few lessons.